Let me check I'm recording. Okay, so good morning, good afternoon, good night, depending on where you are. Today is a pleasure to welcome to Landscape Live speaker, Dr. Audrey Margirier. Audrey is a postdoctoral Marie Curie Fellow, jointly based at the University of Lausanne and the University of Grenoble-Alps. Her research integrates geochronology, low temperature thermochronology, structural geology to better understand the long-term evolution of mountain belts and the processes that shape Earth's surface. Audrey has worked across a range of tectonic settings from the Alps, the Andes to the Colorado Plateau, applying innovative dating techniques to explore landscape evolution over million years. And today we are really happy to have her share insights on her two most recent projects using luminescence dating and low temperature thermochronology. Please join me welcoming Dr. Audrey Margirier. So the floor is yours.
Oh, wow. Thank you for the very nice introduction. So in this talk, I will present two of my recent research projects. So first of all, I will try to answer to the question, what are the processes responsible for the uplift of the Colorado Plateau and canyon incision there? And for this, I used low temperature thermochronology. And this project benefited from the collaboration with many colleagues who helped on the field with the analysis or the thinking of the project. And then I will present you another project that's aimed at answering at the question, what is the duration of sediment transfer within glacial catchments? So for that, we used for the first time luminescence burial dating to date the englacial transport of sediments. And for this project, I really benefited from the collaborative work with Georgina King, Anne Rowan, Julien, and other colleagues from Lausanne and beyond. So understanding the Earth surface topography evolution is really important, as mountain belts and orogenic plateau have a strong impact on global and regional climate. Because of the strong topographic gradient, as well as strong precipitation gradient, there are major sediment suppliers, as well as biodiversity hotspots. So several processes are driving the Earth surface evolution, with including deep-seated processes and tectonics that favor the growth of topography. And the climate is pacing erosion processes and contributes to dismantling topography. It can also have some positive feedbacks with tectonics and deep-seated processes. So at the orogenic scale, the present-day topography and landscapes in general really reflect the past tectonics and erosion history that happened over quite long time scales. However, if we look at the catchment scale, the landscape also really reflects sediment transport and storage, which can happen at time scale that are really smaller, from 1 hour to tens of thousand years. So yeah, just to illustrate a bit the importance of tectonic processes, we really find high topography in mostly active tectonic area with convergent plate margins, along subduction margins, or collision between India and Asia, for example, as well as rift margins, which can be found in Norway, for example, or I think in the eastern Australia. Some of the remaining high topography, orogenic plateau, the South Africa or across the Colorado, are partially explained by mantle upwelling. However, the evidence of mantle activity are sometimes a bit more subtle. So to understand this, here are also a couple of examples on how erosion processes shape the topography. with here the imprints of fluvial erosion on the reliefs. So like a really nice V-shaped valley in Ecuador, and really the vegetation highlights that it's a wet tropical climate, or some other V-shaped valley on the western flank of the Andes in Peru, which is much more arid. So glacier erosion has also a strong, very distinct imprint on the reliefs from high latitude, where we can find some low relief surfaces, to mid latitudes like Switzerland, or low latitudes in Peru, where we can see over deepened U-shaped valley. So to understand how these processes interact, and specifically what processes control the evolution of the topography on orogenic plateau, I will focus on the Colorado Plateau and try to decipher what's the respective importance of mantle processes, tectonics, and surface processes. So here's the dash line highlights the Colorado Plateau. So its elevations are ranging between 2,000 to 2,500 meters above sea level. It's mostly quite low relief surfaces, as you can see on the first picture, and it's deeply incised by the Colorado River system, as you can see on this lower picture that shows the Grand Canyon. So most of the surface of the Colorado Plateau is made by Mesozoic sediments, as you can see here as well. Most of these sediments were deposited at the sea level and uplifted at more than 2,000 meters. So to understand what drove the uplift and the incision, several studies focused on applying low temperature thermochronology in this area. So on this image, you can see both apatite fission track data and uranium, thorium, helium data. So fission tracks are in red and helium are in blue, as the compilation is not really up to date. But it's really highlighting that there is extensive thermochronological data along the Grand Canyon, but not so much in other canyons. So based on this data, people evidence 3 different uplift stages at 80 to 50 million years, 35 to 15 million years, and a more recent one between 6 and 0 million years. However, the magnitude of each uplift phase and the timing of incision are debated, and the processes driving uplift and incision across the plateau are also the matter of debate. Some studies like Lavender and collaborators proposed that mantle processes drove uplift and subsequent canyon incision. So here they propose that a lithospheric removal drove uplift and then incision. Some other studies propose that tectonics is the main driver, and some other study like Dorsey and collaborators propose that a change of the base level of the Colorado River with the opening of the Gulf of, what's the name of it? I don't remember. But yeah, with a base level drop and the change of the base level of the Colorado River system. So orogenic plateaux are a challenge for thermochronologists because we classically use some thermochronometers that are sensitive to temperatures ranging from 120 to 50 degrees for apatite fission tracks and apatite uranium, thorium, helium, which corresponds to magnitude of exhumation ranging from 5 to 2 kilometers for normal geothermal gradient. However, across the Colorado Plateau, the canyons are only 800 to 1,500 meters deep for the Grand Canyon. So it makes it potentially very difficult to constrain incision history using low temperature thermochronology. So this figure illustrates the expected uranium, thorium, helium, and fission track ages for normal geothermal gradient and canyons, such as minor canyons and the Grand Canyon in the middle. So here it really shows that we expect young ages potentially able to constrain incision only for the deeper one. However, because of the Colorado magmatic activity in some area, the geothermal gradient is quite high locally. And then the classical thermochronometers can record a lower magnitude exhumation and potentially, could offer constraint on even like minimally incised canyon. So to focus on a high geothermal gradient area, I went to the Zion Canyon, which is also a very nice place. So in this area, the geothermal gradient was measured in a borehole at 69 degrees per kilometer. And the canyon is incised within some sandstone from the Navarro Formation. This sandstone was sourced from the Appalachians and deposited at about 190 million years. So if we look now at the dates we obtained, so first of all, you can see on the right picture the sample location with Zion 04 on the top of the west rim and Zion 01 at the entrance of the Narrows at the very bottom of the canyon. So now on the plot on the left, you can see like the elevation on the y-axis and the fission track edges on the x-axis. So the top sample is not reset. It's about the age of the source, and the lower sample are partially reset. So fission track ages are ranging from 170 to 300 million years. We are not going to provide a really good constraint on the very recent thermal history, but it will help constrain the whole Cenozoic one. So now for the Ilium ages that you can see are represented with the triangles. So all the Ilium ages are reset, and there is quite a high dispersion of single grain ages for all the samples. So ages are ranging from 3 to 55 million years. And before using them to do any modeling, it's important to understand if something is controlling the dispersion and then if they are useful to predict some thermal histories. So here I plotted the relation between the Ilium ages and the effective uranium content of each grain for Zion 04, 05, and 07. For each of these samples, I dated 4 to 5 single grain. And for none of these samples, we identified an age EU correlation. So it makes it a bit challenging to use these ages to interpret some geological history after. So for the lower sample, Zion 01, I dated 13 single grain for this sample. And here we can see that the lower ages have an age EU correlation, and some of the older ages are likely to be outliers with excess helium. So to better look at this, we plotted the isochronal age, whereas we plot the helium versus the production of helium, and we can see that the 4 younger age are consistent and lead to an isochron age of 5.4 million years. So these individual grain ages can be used to predict the recent thermal history of this profile. Then I implemented all of these thermochronological data into some thermal modeling. So by all thermochron data, I mean, as you can see on the right, like the fission track edges, like that are represented by the blue dots, the track lengths of the samples that are like the red diamonds, and the helium ages that kind of passed the age EU correlation and can be used to understand the thermal history. So then I start the model at 4,000 million years. I put a constraint as a deposition age at atmospheric temperature of the Navarro Formation at 200 million years plus minus 10. And I fixed the final temperature at 15 plus minus 15 degree. So yeah, what we can see here is like just by not imposing a geothermal gradient, our data are like predicting a geothermal gradient of 50 degrees per kilometer, which is quite consistent with data we have. And it predicts a very long residence around 60 to 50 degrees C. Then if we zoom in the more recent part of the history, we can see that there is a reheating that's potentially starting around 20 million years, and then a cooling phase that's starting at 7 million years. So this Cenozoic heating is quite consistent with an elevation potentially of the geothermal gradient during the basin range extension since 40 million years. And the cooling phase is likely to record the onset of exhumation in Zion Canyon. This cooling would imply some exhumation rates ranging from 140 to 200 meters per million years. And it would imply an exhumation since 7 million years of about 1,000 to 1,400 meters, which is quite consistent with stratigraphic information we have. So this data is also consistent with the quaternary incision rates of the Virgin River that was inferred by like dated basaltic flow that were incised, and the incision measurements. So yeah, if we compare that with some other tectonic and like geodynamic data, so the main tectonic activity on the hurricane fault, which is just to the west of Zion Canyon, post-date exhumation in Zion Canyon. And basaltic volcanism that's located in the eastern basin range and like goes toward the Colorado Plateau, started around 15 million years and peaked at 2.5 million years. So both these data like lead us to think that mantle processes might have controlled uplift of Zion Canyon and subsequent exhumation. So to conclude this part, because of the high geothermal gradient in Zion area, apatite fission track and uranium thorium helium thermochronometers can constrain canyon incision. Zion rocks recorded reheating associated with basin and range extension, and the exhumation in Zion Canyon started at 7 million years, likely associated with mantle processes. Then it led us to the question of what are the processes driving uplift and incision in other parts of the plateau. I'm not going to answer to this question right now, but like my current project is about testing the potential of ESR thermochronology to resolve timing and rates of incision of these other canyons. So here on this sketch again, you can see the temperature sensitivity of apatite fission track and uranium thorium helium on apatite, and expected ages for a normal geothermal gradient. And here are a bit the expectations for ESR thermochronometer. So because ESR is sensitive to temperature like ranging from 60 to 30 degrees, it gives us the opportunity to access like the thermal history related to lower magnitude exhumation, such as the incision of moderately incised canyon. So yeah, as I was saying, it's my current project, and I'm not going to develop further on that today. Now to come back at processes that control the Earth surface evolution. The second part of my talk is more focused on the catchment scale, where landscape reflects sediment transport and storage over time scale that are like really shorter. So what's the duration of sediment transport and storage within glacial catchments? So while for fluvial catchments, some new geochronological approaches like meteoric beryllium-10 and luminescence was demonstrated recently as a really useful tool to average sediment transit time and storage and transit time of sediments by Marissa Repash and I think Anne Guilles. These tools have not been developed for so many other contexts. So on the plot on the left, you can see on the y-axis the cumulative transit time, and on the x-axis the distance downstream the river. And you can see that with the meteoric beryllium-10, Repash and collaborators really managed to identify the variation of transit time and overall increase of transit time of sediments toward downstream. So for glaciated catchment, while many studies focused on glacial erosion because it's a very efficient erosion process, and some studies focused on constraining the subglacial sediment transport, there are really like no data about the englacial sediment transport. And also it's really hard to know how long the sediments are stored within glacial catchments. So under the current climate change, like glaciers are shrinking and there are more and more debris covered glaciers. So it's really important to constrain englacial sediment transport, and also to understand like how efficient are glaciers compared to fluvial system to transport sediment downstream. So for this part of the study, I focused on the Miage Glacier, which is located in the southern part of the Mont Blanc Massif in Italy, near the border with France. You can see that the Miage Glacier results from the convergence of the Bayernese Glacier, the Dome Glacier, and the Mont Blanc Glacier, and is flowing down towards the south and is then forming 2 or 3 lobes at its terminus. So we picked this glacier because it's really heavily debris covered, as you can see on this picture. So there is, I promise you, there is still ice below these rocks until about the terminus here and here. And the catchment is gneiss and schist mostly. We use the luminescence dating to constrain sediment dynamics and like sediment burial. So how does luminescence work? So you can see this sketch is representing like a crystallographic network with some traps area that are located in defects and impurities. So under ionizing energy, the electrons can get trapped in these crystal defaults. And so the longer they are exposed to natural environmental ionizing energy, the more electrons are getting trapped. And then if we add energy to this crystalline network through light or heat, there is an electron hole recombination, and the electrons are getting detrapped and emit heat or light. So to have a more friendly sketch, we can take like a crystal network or the traps as a battery analog. When it's exposed to light or heat, there is no trapped electron. If there is a burial and we don't provide light or heat anymore, and it's exposed to environmental radiation, the trapped electron population increases with time. And then if we expose this crystal to light or heat, the trapped electron like decrease. So in the lab, the luminescence signal is measured using a photo multiplier tube that you can see here in black. And the targets are like quartz, feldspar, or also multi-minerals in our case. So in the lab, we stimulate the sample, and through the stimulation time on the x-axis, the luminescence signal is like quite high at the beginning and decrease rapidly with time, because at the end, no electrons are trapped anymore. So now I will explain you a bit the principle of luminescence rock surface burial dating applied to quantify the burial duration of englacial sediments. So first, the rock is exposed on the head wall of the glacier. And then on this graph, you can see the luminescence signal on the y-axis. And on the x-axis, it's the depth within a sample. So from the surface of the sample on the left towards the inner part of the sample on the right. So here you can see that the sample is exposed to the light, and at the surface, the signal is zeroed by the light exposure. And at depth, the signal is saturated because the light didn't penetrate in the clast. So then, if the rock is falling into the accumulation zone of the glacier and is getting buried, then because of the environmental radioactivity, the signal is increasing at the surface. And the longer the transport is, the greater the signal here is. So we sampled 18 rocks embedded in the ice of the Miage Glacier. You can see like the black markers, like the squares are the samples. Here are like some pictures of the sampling sites for different samples. You can see that we already picked clasts from various sizes but are really still embedded in the ice. And we worked with part of the rocks that was still like really in the ice and not exposed to the light after in the lab. So then the sample processing is involving some coring of the unexposed faces, some slicing of the cores to have the luminescent signal at various depths. And then we can do the luminescence measurements on these slices. So here are the luminescence signals I obtained for 3 different samples. So you can see that for the first one, we can see a nice horizontal plateau that's indicating that the samples was well bleached before being buried in the ice. And for the 2 other samples that are like on the right, there is no horizontal plateau, and the signal is increasing quickly and reaching saturation level. So only out of the 18 samples, only 9 samples show a plateau and can be used for dating. Then we can use this part of the sample to determine the age, like the burial duration of this sample, which is equal to the equivalent dose, so the amount of electrons that have been trapped over the boreal time, divided by the environmental dose rate, which is like kind of the charging time. Again, we can see a little battery analogy with the amount of charging and the kind of speed of charging. So this equivalent dose can be determined doing a dose response curve in the lab. So we expose the sample to different doses and see the amount of luminescence that we record in the lab. Then we can infer the equivalent dose by fitting the natural signal we get. And the dose rate is determined using uranium, thorium, and potassium concentration from the rock. I'm not going to develop on this. So here are the ages we obtained. So on the x-axis, you have the distance from the glacier head wall, and on the y-axis, the ages. So ages are ranging from 0 to about 5,000 years. And you can see that in the upper part of the ablation zone, so between 2 and 5 kilometers, we have some younger ages, while near the terminus, we have older ages. So then we compared our luminescence ages with some ages obtained through glacier modeling. So for this, we did a simulation of ice flow and glacier evolution using isocia. And this model is using a particle tracking scheme to simulate erosion in the head walls, transport, and deposition of sediment. So the simulation duration is here like 12,000 years. And we forced it to present the observation using the temp 12K paleo temperature record. So yeah, you can see here the temperature forcing and the glacier evolution with the ice thickness and the spatial extent of the glacier that is varying. So yeah, then just to validate that our modeling is still a modeling, but approximately correct, we compared the simulated ice thickness with some estimations from Farinotti and collaborators. And we can see that the model is like fitting pretty well the estimated ice thickness. And we compared the surface velocity of the model versus the estimation from Milan and collaborators. And yeah, here, while the pattern is pretty similar, there is quite a little offset between the simulation and the observations. But I want to highlight that in these catchments of very thin ice, Milan and collaborators find quite high flow velocity, which might not be like perfect. So yeah, the model fits pretty well the present day observations. And then we can have a look at the predicted particle flow lines and the transport duration. So on these two figures, the near surface flow lines are represented in blue. The near bed flow lines that you can better see on the right graph are represented in black. And the short flow lines that we are not going to use too much are represented in red. So now if we look at the simulated glacial transport time predicted by isocia versus like the luminescence ages, we can see on this graph that it's mostly fitting pretty well, although we don't have so many age prediction by the model at distances from the head wall from 2 to 6 kilometers. So yeah, in this in the right plot, which shows the luminescence burial ages versus the simulated glacial transport time, like the red bars are indicating the like luminescence ages, as well as the mean glacial transport time, while the black bars, are indicated the maximum predicted transport time for like the 5 closer particle from the sampling site. So yeah, luminescence ages are in pretty good agreement with ages predicted by ISOCIA, and the duration of transport vary from 0.2 to 5,000 years. So how does this duration of englacial sediment transfer vary from a catchment to another? Like, are our data representative somehow of several catchments, or because it's so debris covered and the lower part of the glacier is a bit stagnant, it's completely overestimating that. So for this, we can compare the Miage Glacier, which is south-facing, with the Mer de Glace glacier, which is kind of a bit more healthy, with like a nice north-facing slope with mainly clean ice. So this was the work of Léa Rodari, who did their master thesis at the University of Lausanne. And she dated the multiple samples from the ablation area of the Mer de Glace. And I jump directly into the comparison of Mer de Glace and Miage. So here again, on the y-axis, you can see the boreal duration, like our luminescence ages. And on the left, on the x-axis, it's the distance from the glacier head wall. So like the ages are in the same order of magnitude. And while for Miage, only 40% of the clasts were transported or stored for more than 1,000 years. For the Mer de Glace, 70% of the samples are older than 1,000 years. Yeah, again, like the Mer de Glace ages are ranging from 0.6 to about 7,000 years, which is very similar to the ages of Miage, which are ranging from 0 to 5,000 years. So yeah, we can conclude that luminescence rock surface burial dating can constrain duration of englacial transport of clast. Surprisingly, the duration of rock clast transport varies from about 200 years, mostly for near surface ice transport, to about 6,000 years for close to the bed transport. The total duration of rock class transport may encompass some storage phases within ice aprons or ice marginal moraines. And yeah, to provide a more general conclusion, low temperature thermochronology and trap chart dating are opening new avenues for addressing long-standing geologic questions. With luminescence, we could for the first time quantify the englacial sediment transport and storage duration, while classic thermochronological methods allow to constrain low magnitude exhumation in high geothermal gradient setting. So now there is still the remaining question of can ESR record incision of canyons across the Colorado Plateau? But yeah, I leave it here and I will hopefully answer to that in the next presentation. Thank you.
Thank you so much, Audrey. That was an amazing talk. Thank you so much. We just have opened the chat for questions. You can type your question or you can raise your hand if you want to unmute yourself and ask the question yourself. So while we wait for people granting their questions, I have a question that I would like to ask you. So it was in the first part of your talk in the Zion Canyon when you were showing us this plot with the low thermochronology ages and the dispersion. I think it was like the apatite helium. And you chose that it was a correlation between the effective uranium and the age. And a lot of them were, they did not have this correlation. So you said that they were not significant to interpret them geologically. And I was wondering if that they don't have a correlation, but can they tell you something about why they don't have, like what happened to these samples that they don't have a correlation, or what happened to this grain that can help you to get constraints on the history of these samples?
Yeah, I guess for such a as it was far away, that far back. Yeah.
Yeah.
So yeah, I guess there are, it's not all well understood, like the dispersion, or like there are, yeah, several potential problems or factors that could influence dispersion, or like kind of ages that are a bit too old or a bit anomaly old. You can have some ilium implementation from neighboring grains. This is like something that could be particularly influencing a lot the ages for ages with low EU content. And then it's also the question of I guess our current models to explain ilium diffusions are working well for nicely behaved age-EU relationship, but improving these models could maybe then allow to better understand the ages that we consider right now being just with excess EU. Yeah, and here as well, there is quite like an interesting sample like Zion 04, which is not showing a nice age-EU trend, but the ages are not so dispersed actually. And it's weird because it's a sample which is like really at the top of the profile, and it's showing these not so old ages compared to all the rest. And it's pretty hard to reconcile with fish and track data. So yeah, I'm trying to explore a bit that, or I need to answer a bit better to this question before getting further with this data set, I think.
Thank you.
I see Sean raised his hand. I don't know if you want to unmute yourself.
Yes, can you hear me?
Yeah.
Okay. My camera doesn't unmute, but first I have to apologize that I only heard half of your talk and then my Zoom crashed, and so I missed most of the end. But I think I got most of the Grand Canyon part, and so I'll limit to that. I have two questions, if I could. And in the next slide here, you actually calculated an isochron age, right? Is that yeah here? Is this for one of your samples, or how many of the samples did you end up using isochron ages for then?
Yeah, it's an easy question. Like we can only I could only calculate an isochron age for one sample.
There, that's the next one.
Because it's the only one which has grain behaving nicely. Like all the other ones, I mean, I didn't try, but as there were no age EU correlation already, it was a bad start to try isochron age. To me.
Yeah. Okay. So in fact, in the end, the excess uranium didn't really help solve the problem. It's also this isochron age is very young then compared to the others, isn't it?
Yeah, I mean the younger ilium ages are pretty young as well, so it makes sense.
Okay, although I would think that because they actually are fairly clustered in that sort of 10 to 15 MA range there, the dispersion isn't that high. It's more the dispersion of the relationship with elevation that's not very well defined.
Yeah, I mean it's not super dispersed, but by squeezing a bit more the EU scale, the age EU relationship would then get crazy steep. If you see,
doesn't look like it's really something to be solved by EU or excess uranium.
Yeah.
Anyway, my other question though is on the next slide, your thermal QT modeling that you did. Did I understand that the geothermal gradient from the first phase there, sort of 200 to 20 MA, was very close to the modern geothermal gradient?
Yeah, or like, so yeah, like the modern geothermal gradient is about like from the closest well is 70 degrees per kilometer. And when modeling, we infer based on the data a geothermal gradient of 50 degrees per kilometer, which is consistent or like relatively consistent. But then like in this modeling, I allow the geothermal gradient to change, so it's the same for the whole modeling. Except
but that's what I would expect, that because the thermal event in the late history is a sort of conductive increase in geothermal gradient, I would think that the modern high geothermal gradient is probably reflecting that event, but in fact, then the early gradient should have been much, much lower. Sort of more normal 25, 30, something like that, right? So I'm sort of surprised that the gradient, that the high gradient in the early history doesn't seem consistent with the modern high gradient if you want to have a big thermal event occurring at 10 or 20 MA.
I mean, again, I don't leave the possibility here in the modeling to vary the gradient. Then like the data are kind of converging toward a gradient of 50 degrees per kilometer for the whole story. But by allowing the gradient to change.
Did you model the sample simultaneously with QT, or are they modeled independently? They're modeled simultaneously then.
Yeah, it's all together as a vertical profile.
Okay, so then it doesn't really let you change the geothermal gradient. It seems like it would be better to have the model general enough to increase the geothermal gradient if you want to have this conductive event that occurs at 10 to 20 MA.
Yeah. Like right. That's a thing I was exploring a bit, and I need to explore a bit further.
Actually, so if I may, I'll just say. Go ahead. Just saying that we have another question from Lon Abbott, and maybe we can continue the discussion this way. That actually is on that same slide, and I think it corresponds to the same discussion. Asking about the Zion thermal model, which shows a slow cooling throughout the Cenozoic during a time when sediments were accumulating regionally. I would expect warming at that time and not cooling. Could you comment on that seeming discrepancy?
Yeah, so I think we don't have so much resolution to see like the multiple like burial and exhumation events that must have happened between 200 and 50 million years. I saw that there are like, new sediments on the plateau accumulating at that time. There are also discordance within these sediments, but we don't have the resolution for that. And like the pastel colors, like highlight the uncertainties of the model. And I guess within that, you could have like, wiggly cooling and reheating.
Yeah, you could even almost fit a progressive warming within this envelope of uncertainty.
Yeah. It's like, I guess what I would take out of this is rather like the samples, or like the lower sample is remaining at about 60 to 50 degrees, plus minus 20 within this time, rather than really saying much, or saying that, I should not say that nothing is happening, but we don't really record it.
And could you remind us when this warming happens linked to a potential change in the geothermal gradient, what is this new value of the geothermal gradient once you start to have this activity of the basin and range? Like roughly, because my brain got switched to glaciers, so I need to
so I mean the basin and range like activity in this region is starting around 40 million years, and we can really see the warming starting at 20 million years. So it might be related rather to an acceleration of the extension rather than really the onset. But
okay, right.
Thanks, Audrey. We have a question in the chat from Lenka. So it says, thanks for your talk. I was wondering if you use ISO/SIA for predicting sediment flowiness as well. And what will your recommendations be for modeling sediment transport based on luminescence in arid climate? So knowing glaciers necessary.
So yes, or like I used isocia, like we used isocia, or Anne Rowan used isocia. I give her the full credit for the isocia modeling. And we did use isocia for predicting sediment flow lines and predicting the duration of transport until the clasts are exposed at the glacier surface. What would be my recommendations for modeling sediment transport based on luminescence in arid climate? Oh wow! Like I guess what context? I guess it really depends of the question. If it's about the fluvial transport time or storage, like I guess there are two approaches that have been developed for fluvial setting, like the one developed by the team in Toulouse. That's kind of probabilistic resetting of single grains during their like journey downstream, like a fluvial system. And there are some models from Harrison Gray as well, like kind of based on the bleaching of sediments toward like downstream. I think it's complex and there is still a lot to be done and to explore. Not sure about my advice. Maybe contact the people, or like even the people in Lausanne who are more doing a fluvial setting rather than me. But yeah, thanks for your question.
Maybe I also have one question related to the second part. And so also thanks a lot for the nice talk. So at the end you compare two glaciers that are kind of different. I was wondering, like, did you assume, so for the dose rate calculation, did you assume the same dose rate in both settings, although one glacier has way more debris than the other, or how did you deal with that?
We calculated the dose rates individually for each class. Like for the Miage class, we especially as the lithology were like so like different from a class to another. We really did like individual geochemical.
But for the environmental, like outside the class,
outside the class, we consider it ice. So
okay,
like
it's ice. Yeah. Okay.
Zero environmental input.
Did you test if things would change when using something else?
I mean, yes, like for the surface slice, for sure.
Okay.
But like kind of we really know it's at the edge between the no dose to like some materials providing a dose. So I think it makes sense to calculate it this way.
Yeah.
Well, I would have another question. Maybe I can squeeze it in before the hour about the glacier. If I understood correctly, when you were plotting your age versus distance from headwall data, the assumption there is that the velocity field is going to stay constant over the last several thousands of years. Can you, with the data that you have, resolve, for example, an acceleration in the transport rate or a deceleration of the flow rate through time? Do you need some additional pieces of information, or is that a question that could be resolved with simply more of these glacial rafts?
So yeah, I think we were initially very surprised of these old ages, if we already only look at the ice age, it's really younger. Like if it's only the ice traveling, or if the boreal age would be only relative to the fast ice traveling really in the glacier, ages would be really younger. So I think for most of the class, very some storage, or luminescence ages are capturing some storage. And I guess with more dating, we could understand better what's the timing of storage and where it's happening, or when and why. But the ice dynamic itself for such kind of small alpine glacier, I don't think luminescence would help. Or with the sampling strategy in Miage, we really expected to have a linear correlation with distance along the ice, with getting progressively older ages, but it's really not happening.
And so along Miage and along Mer de Glace, can you identify the different provenance points of the clasts, or is the lithology uniform enough that you cannot say exactly whether the clast initially eroded, whether it is at the bed or at the head wall, or the flanks?
Yeah, so on the Mer de Glace catchment, all the head walls in the accumulation area are granite and very, I guess, not distinctible. So that's why we use ice flow modeling and particle tracking to try to see from where the clasts are coming from by this means. And for Miage, there are several lithology, but it's rather super messy catchment, and I would not use lithologies to really pinpoint from where it's coming from. It's rather the modeling that's giving us some clue about it.
Okay, understood. Thank you very much.
Yeah, you're welcome.
Thanks so much, Audrey. We are around the hour, so we just want to thank you. That was an amazing talk and a great discussion. Thanks everyone for joining us, and for the ones that are watching this on YouTube, please continue watching our seminars. I'm trying to remember who is next week. 1 second, I'm going to announce it. So next week we have Jing Dao Lai. They will be presenting landscape trends and response times in glaciated mountain ranges. So if you want more about glaciers, please come for our next week's seminar. That's all for today. So thank you so much, everybody. Thanks for joining us.
Yeah, thank you so much.
Thanks, Audrey.
Thanks, Audrey.
See you soon.
Bye-bye.
Yep.